Hello. In today's lecture, we're going to be talking about Lecture 4, or we're going to be bringing up, summarizing Lecture 4, which is the last lecture within Chapter 2. Here we're going to be looking at isotopes a little bit. We're going to look at ionic compounds versus covalent compounds, a little bit about the periodic table. We're going to look at pi atomic ions. We're going to look at naming of ionic compounds, naming of some covalent compounds, along with naming of organic compounds, a specific type of covalent compound. So, first thing I want to talk about is the number of subatomic particles, or determining the number of subatomic particles. We talked about this a little bit already, but I wanted to go ahead and give you guys a formula for it. So we can determine the number of protons, neutrons, and electrons based on information that we have. So if we have our mass number, it's going to be equal to the number of protons, or our atomic number, plus our number of neutrons. Remembering that our mass number, number of protons, number of neutrons, we're talking about basically an AMU. And then if we're talking about our charge, it's going to be equal to our number of protons minus our number of electrons. So with both of these formulas, we can determine all of our different subatomic particles. We want to talk briefly about elemental symbol. Again, this is something we've already kind of covered, but I'm going to need it for this to talk about isotopes. So an elemental symbol will have a mass number, an atomic number, and an elemental symbol. So a letter or letters. So with isotopes, each different isotope will have its own individual elemental symbol. So, for instance, if we're talking about carbon-12. Carbon-12 means that we have the isotope that has a mass number of 12. So, our mass number here would be 12. Our element symbol would be C, and our atomic number for carbon is 6. So this means our mass number is equal to 12. Atomic number, which is our number of protons, is equal to 6, and then our number of neutrons, if we take our mass number minus our atomic number, gives us 6. So anytime we look at the periodic table, what we're looking at is an average of those isotopes, and we call that average atomic mass. That's what's on the periodic table. And that the unit for that is AMU if we're talking about kind of the atomic mass of isotopes, or grams per mole. They'll be the same. But AMU, we're talking about just atoms. Grams per mole, we're talking about lots and lots and lots and lots of atoms. Okay, so to determine our average atomic mass, it is going to be the sum, which is this funky looking little e, of each of the isotopes' mass times by their fractional abundance. So you'll sum each of your different isotopes, whether you have 1, 2, 3, well, you have to have at least 2, 2, 3, 4, and so on. You'll sum their isotope mass times their fractional abundances, keeping in mind that the sum of our fractional abundances will be equal to 1. So if you have two isotopes, for instance, you can call X one of their fractional abundances, Y the other one, and when you sum those together, you will get a fractional abundance equal to 1. So let's look a little bit more at our periodic table and its arrangement. There are many ways of arranging the periodic table. In a further chapter, we'll look at alkali metals, alkaline earth metals, chalcogens, halogens, noble gases, lanthanides, actinides, transition metals, noble metals. We'll look at the pycnides and all of those things within our periodic table. But for today, we're just going to look at breaking our periodic table down into metals, nonmetals, and metalloids. So if we look at our periodic table, it looks something like this. And we have metals, nonmetals, and metalloids. So our metals are the things on the left side of the periodic table. Our nonmetals are the things on the right side of the periodic table. And then our metalloids are the things on the stair step right in the center. They're right between the two. Where metals or metalloids are kind of properties between that of a metal and a nonmetal. And now that we know where things are on the periodic table, we could use that excuse me, we can use that information to look at covalent compounds versus ionic compounds. So when we talk about a covalent compound, we're talking about a species that it's made entirely of nonmetals. An ionic compound, we're talking about things that are made up of a metal or metals and nonmetals. So we have both metals and nonmetals in here. So metals and nonmetals combine to make an ionic compound, where our metals become cations. So they have a positive charge. Cat. Pause. And then our nonmetals are anions, or become anions, with a negative charge. So ionic compounds are made up of ions. Our cations, which have positive charge, our anions, negative charge, and it results from a transfer of electrons from one species to another. Again, a topic we will discuss more in detail later. Okay, so now that we know what type of compounds we can have, what kind of molecules we can look at the chemical formulas of them, which tells us atom types within the structure. So it's going to give us all of our atom types that are within there. And those different atom types can distinguish between different types of molecules or compounds. And then within our chemical formulas, we can have two different types. We can have a molecular formula, and we can have a empirical formula. Our molecular formula is specifically for molecules. So our covalent compounds, or covalent substances. And here, our molecular formula is going to show not only the different types of atoms, but exactly how many are in there. So it shows the actual amount of each type. And then our empirical formula is going to show the smallest whole number ratio. To get to a molecular formula, or to get to an empirical formula from a molecular formula, so the empirical formula is calculated from the molecular formula by dividing the molecular formula by the largest common factor. Generally, empirical formulas can be used for either molecular species or ionic species, but they're the only way to show an ionic species. So ionic species are always given as molecular formulas. Empirical formulas. And that's because ionic species are a extended structure, while molecular species are a very specific structure. So they're a little different in nature. Because of the way that ionic compounds are formed, there are a bunch of ions put together. They are going to be held together a little bit more strongly than molecular formulas. So they're going to have different properties than molecular formulas. So I'm not going to go super into detail about the properties in this particular video, but they're going to be high melting, solids generally. They're going to be brittle and hard. They're going to be almost always soluble in water. H2O, that's our molecular formula for water. It's also our empirical formula. And then they're going to be insulating as a solid. Ions are formed by the transfer of electron from the metal to the non-metal, which is why the metal forms a cation, because it's lost electrons, while the non-metal forms an anion because it has gotten an electron. So if we take sodium solid plus chlorine gas, they produce sodium chloride, which is a sodium cation and a chlorine anion. So the periodic table is a great resource for determining what type of ions we would form. So if some metals form specific cations, while some nonmetals form specific anions. And like I said, we use our periodic table to determine that. But just as a note, for our metals, if we have group 1A, it'll form +1 cations. Group 2A will form +2 cations. And then group 3A, or it's also shown as 13, will form +3 cations. With our nonmetals, group 4A, or 14, doesn't form anions. So just completely ignore that group. Group 5A, or 15, is going to form -3 anions. 6A, or 16, -2 anions. Group 7A, or 17, -1 anions. And then group 8A, or 18, is inert. No anions. And no anions, not non-anions. No anions, and they usually don't form covalent substances either. So when we're talking about our formation of our anions, we're talking specifically about ionic compounds. If we're talking about a covalent compound, we don't have ions, so our nonmetals are not going to form these anions. So we use our periodic table to determine this, and the whole idea is to try and get 8 electrons. So either by losing electrons or gaining electrons, we can get 8 electrons in our, what we call our last shell. So that's why things lose or gain electrons, is to get to a specific configuration to be happy. We're not going to talk much about this. For right now, just memorize what we form. With transition metals, are these right here. These are transition metals. These are going to form variable charges. So in general, we can't actually use our periodic table to determine what charge those are going to make. We also have what's called polyatomic ions. And these have set charges, and we call these molecular ions. And there is a table on the PowerPoint of the ones you need to memorize. It's slide 31 or so, so memorize these. And there's different anions and cations on there, and what you'll notice is that they're all, for the most part, molecular in nature, which is why they're called molecular ions. And whenever we're making an ionic compound, we have a cation and anion, so make sure with your ionic compounds, these need to balance. So there needs to be a neutral species at the end. Okay. Your ionic species is going to have the cation first. And it's going to look like this, where we have AX, BY. And you're going to want to have a ratio of these so that your overall charge is 0. So make sure that if you take X times by the cation charge plus Y times by the cation charge, or sorry, the anion charge, this equals 0. Okay? And the easiest way to do this is if you have A and plus B and minus, you get AN BM. So you're basically taking these and making them the subscripts there. Last thing I want to talk about is naming. And I'm going to be very brief with this because there will be all of the rules for this in your packet. But naming, we call this nomenclature. So you'll hear that term in the future. Nomenclature is based on IUPAC system of naming. And it's just a way of naming. And it's in order to get a specific name that is only referring to one substance. So no common names are generally they're not used within there. So let's look at inorganic ionic species first. So the cation is first, and it retains the atom or polyatomic name. Okay. And then, as a note, if your cation is a transition metal, the charge also needs to be indicated. The charge of the cation must also be indicated. And it's done so using a Roman numeral. Which is equal to the charge. Okay. So we have something like sodium. We just call it sodium. If we have something like iron 3+, iron is a transition metal, we'd call it iron 3. After you name the cation, the next thing you name is the anion. And you're either going to name it, if you have NH4+, a polyatomic, it's just called ammonia. Ammonium, excuse me. Okay, next we name the anion, and the anion is going to be named with an IDE ending if it is just a regular anion. So regular anion, IDE ending. Replaces the normal ending. Of the atom. And then if you have a polyatomic, it's going to retain its name. So if you have something like O2- as your anion, this would be oxide. So oxygen becomes oxide. If you have something like N3-, nitrogen becomes nitride. So that IDE ending. And then, of course, if you have some sort of polyatomic, such as OH-, this is called hydroxide. Or CN- cyanide. Please look over those polyatomics. You must have that memorized before our test. So get all of those named and in your brain. We'll talk about them a little bit more in class, making sure that you guys are aware of all of the polyatomics you need to have memorized. Okay. The next thing we're going to look at naming is acids. So acids are an anion plus positively charged hydrogens. And we call these protons. So we balance out our anion charge with our protons. So if we have a 2- anion, we need to add 2 H+, so that we can overall 0 charge. So our anions, or our acids, are going to be named based on the anion. So we look at our anion ending, and we change it by adding in H+ to the acid. So if we have an IDE ending, such as chloride, oxide, bromide, we would add in hydrogens until we get hydro. Same thing here, ic acid. So we add a hydro prefix and ic acid suffix. So we lose the IDE, get ic acid. If we have an ATE ending, and this is going to be one of our polyatomics, we add in our protons, and we get ic acid. And then last, if we have an ITE ending, we add in protons, and we change our ending to us acid. So we're just changing the suffix, except for in the case of an IDE ending where we change it to ic acid. Okay. Next thing, one of the last things we're going to talk about naming is binary molecular compounds. Here, we're going to have a prefix which indicates the number of the substances. So we're going to have M, X, N, Y. The X is the number of atoms of M. Y is the number of atoms of N. And you're going to base the prefix on these. Again, there's a chart with your different prefixes. 1 is mono, 2 di, 3 tri, tetra is 4, 5 is penta, so on and so forth. Make sure you memorize those. So with your first element, so the one that's written first, it's going to have a prefix that gives a number, and then its element name. And then the second element, it's only binary, so we only have a second, 1 and 2. Element, not electron. It's going to be prefix plus name with IDE ending. So for instance, if we have Cl2O, this would be dichlorine. So we keep the first one, the element name, and then monoxide. If you have two O's together, get rid of it. If you have an A and an O together, get rid of the A, those type of things. We'll go over the whole set of rules soon. Okay, so that is how you name those. A note, though, for the first element, never use mono. So if you have something like NF3, this would be nitrogen trifluoride. So you never use the mono if it's the first one. And then if you have a prefix with A or O, and the element starts with a vowel, drop the A or O. Okay, last thing I want to talk about very quickly is organic compounds. So these are going to be carbon and hydrogen containing. There's a whole branch of chemistry that talks about organic compounds. We'll talk about them in class much more in detail, but I just want to talk about their naming real quick. So for the naming, it's based on the number of carbons. Okay, so you count number of carbons, and you're going to use a prefix. For simple alkanes, these are things without any double bonds. It's going to have a suffix of ANE. So if you have carbon, 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 so a simple carbon-hydrogen chain, like so. There is 1, 2, 3 carbons, so this would be propane. And again, there is a chart within the PowerPoint that has all of the ones. You guys are not required to memorize that one. That will be included on your sheet if we do any alkane naming. Okay, that's everything. I will do some mini lectures within class and make sure that you have all the information you need so you can complete the worksheet during class, and that's about it. Sorry this is so long. Bye, y'all.